Beneath the oceans, a vast network of conventional optical fibers forms a global nervous system, silently transmitting the data that keeps modern communication alive. These fibers are a triumph of engineering for one specific reason: they possess massive bandwidth, allowing them to carry a specific fixed wavelength of light across thousands of miles of ocean with almost no signal loss. Conventional fibers trap that light by layering two chemically different types of glass together, an inner core and an outer cladding. Because they rely entirely on this chemical contrast to guide the light, it is extremely difficult for engineers to tune or alter the light's physical properties. To build compact, advanced optical devices that force light to react and change its frequency, standard fibers are incredibly inefficient. Their low nonlinearity means you have to use massive lengths of cable and pump in enormous amounts of peak power just to trigger a reaction. The exact two-material system that connected the planet is now the physical bottleneck preventing the creation of compact, advanced optical tools. To bypass this chemical limit, physicists abandoned the two-material system in favor of a single material structure called a photonic crystal fiber, or PCF. This cross-sectional diagram reveals the defining feature of a PCF. Running down the entire length of the fiber is a highly precise, microscopic geometric pattern of air holes. By adjusting the diameter and spacing of these microscopic air channels, engineers create an artificial structure that traps light. This geometry concentrates the electromagnetic field into an incredibly dense area, forcing it to interact intensely with the surrounding glass. This shifts the focus of the engineering. Instead of searching for new chemical compounds to control optics, physicists can now manipulate light purely by designing geometric space. This schematic outlines the actual manufacturing process, stacking silica tubes into preforms and drawing them out into finished fiber. Physically constructing these complex, honeycomb-like structures is highly precise and expensive, making trial and error on the factory floor impossible. Before a single strand of glass is drawn, engineers rely on a powerful computational workflow to test their designs: the finite difference time domain, or FDTT, simulation. FDTT translates Maxwell's equations, the foundational rules of electromagnetism, onto a three-dimensional digital grid. This allows computers to calculate exactly how light will behave inside any proposed geometric lattice. The algorithm computes these fields using a leapfrog mechanism. First, it calculates the electric field components. Then, using that data, it evaluates the magnetic field. It steps forward through time, back and forth, tracking the light's propagation across the grid. This digital environment serves as a virtual laboratory. It empowers physicists to experiment with complex air hole arrangements and perfect a fiber's geometry long before the physical manufacturing stage begins. The ultimate target for many FTDT simulations is finding a precise geometry that triggers a rare optical event known as supercontinuum generation. This line graph illustrates exactly what a supercontinuum is. The narrow blue spike represents an initial single-color laser pulse. The broad red area shows the continuum, where that pulse is forced to widen into a massive spectrum containing multiple colors. These FTDT plots test if proposed geometries trigger violent nonlinear processes, like Soliton vision. On the left spectral heat map, the initial pulse rapidly splits into new wavelengths, visible as aggressive redshifts. On the right temporal heat map, the beam physically fractures into distinct trajectories. These heat maps are the mathematical roadmaps engineers need. They prove that a specific arrangement of microscopic air holes will successfully force light into a high-energy chain reaction. This transverse mode profile displays the optimized result of that computational workflow. Here, an optimized photonic crystal fiber design traps a high-intensity light pulse within exactly 11 carefully calculated rings of air holes. By meticulously adjusting the diameter and pitch of these holes, engineers achieve immense nonlinear coefficients. The geometry also perfectly flattens the dispersion, how colors of light spread out, at standard telecommunication wavelengths like 1550 nanometers. These density plots verify the physical compression this lattice achieves. Notice the vertical axis. We are witnessing a full ultra-broadband supercontinuum generated over a distance of just 15 centimeters. The FTDT workflow successfully bypassed the physical limits of conventional glass, allowing engineers to accomplish in mere centimeters what used to require kilometers of traditional fiber. Out of the digital laboratory and into reality, pumping a laser into one of these highly nonlinear PCFs instantly generates a blinding multicolored spectrum. This multi-octave light is the core component of ultra-precise biomedical sensors, atmospheric monitors, and the next generation of wavelength division multiplexing for telecommunications. These fibers are especially critical in high-stakes environments like surgical suites. Here, the unique geometry of the PCF is used to deliver high-power, continuous wave lasers directly to delicate tissues with absolute precision. By mastering the computational workflow of the photonic crystal fiber, engineers have moved beyond simply improving data cables. They have rewritten the physical rules of optics, turning rigid glass into a blank canvas for designing light itself.